Welcome back to the video series on integration and differential equations. Today we're going to look at a shortcut for integrating the ln form. Let's start with an example. Suppose we want to evaluate the integral of dx over 3x plus 4. So let's do it the usual way through substitution, and then once we've done it the long way, we'll see if we can develop a shortcut. So in order to get this looking like the ln form, we need to make a substitution, and the correct substitution would be to let u equal the entire quantity in the denominator. So we'd let u equal 3x plus 4. du would then be 3 times dx. And we could look back up at our integral and say, all right, so we've taken care of the denominator. We're going to be able to rewrite that as u. And we would need to know how to rewrite dx. So to move from 3dx to dx, we're going to be dividing by 3. du over 3 is just another way of writing dx. And with that, we can rewrite our integral. So the integral in the question is equal to the following. We could rewrite the dx as du over 3. So I think I'll put the 1/3 out in front of the integral. And in the denominator, we're just replacing that denominator with u. So there we have the classic ln form, and if we remember integrating the ln form earlier in the course, we know that we're going to get 1/3 times ln absolute value of u plus a constant, and we could go back to our original variable. We'd have 1/3 ln absolute value 3x plus 4 plus a constant. So let's see if we can come up with a shortcut to move from the original problem down to this line here. Well, we had to recognize first of all the form of the integral. We had dx over some number times x plus a constant. And we're saying that when we integrate this kind of expression, we're going to get pretty much something that looks like ln absolute value of the denominator and of course plus a constant. But the real question is, where does this 1/3 come from? So if we trace this back through the substitution, the 1/3 came in this step here. And tracing it back through the previous steps, it came because we had a 3 over on this side. That happened because 3 was the coefficient of the x. Alright, so it looks like out in front of the line we're going to have 1 over some number, and that number is going to be whatever the coefficient of the x is. So let's see if we can formalize this in terms of a shortcut. What we're saying is that if we want to integrate dx over something that looks like ax plus b, then we're going to get pretty much ln absolute value of the denominator, but we're going to have to correct by going 1 over a, where a is just the number sitting in front of the x there. A is the coefficient of the x inside the original denominator, and then we'll say plus a constant. In this context here, a and b can be any real numbers that we like. The only restriction is that a should not equal 0, otherwise we would be dividing by 0 here. Alright, so let's do a few quick examples, just make sure that we understand the shortcut. So let's say someone asks us to integrate dx over x minus 3. We'd say, okay, shortcut applies because we've got something of the form ax plus b in the denominator there. So we are going to get ln absolute value of the denominator plus a constant. And we need to think here about whether we need to correct the coefficient. So the coefficient of the ln here would be 1 over the original coefficient of the x. Well, the original coefficient is 1. So no, we've just got 1 over 1. We don't really need to write that down. So similarly, if you were integrating dx over, say, x plus 5, same sort of thing. You'd have ln absolute value x plus 5 plus a constant, and notice that the coefficient of the ln is still just 1. So the situation where we'll have to be careful is if we integrate dx over, say, 2x minus 9. See, now we've got a coefficient of 2 for the x, so we're going to have to correct the coefficient of the ln. We're going to have 1/2 ln absolute value 2x minus 9 plus a constant. Okay, if someone asks us to integrate dx over, say, x squared plus 1, we would say shortcut does not apply. So let's just be very clear that the shortcut only applies when you've got a linear expression in x, meaning something that looks like ax plus b in the denominator. Doesn't apply when you've got something like an x squared or square root or anything other than this specific form. So in fact, you may remember from previous discussions in the course that when you integrate dx over x squared plus 1, what you're actually going to get is arctan x. So certainly the shortcut does not apply in this case here. Okay, I think we'll see in the next video that the shortcut is going to make our problems go a little bit faster when there's more of an involved process going on. So thanks for watching, and we'll see you in the next video.